Hello, so today I'll be explaining to you our project, Smart Toaster Finite State Machine, a digital hardware simulation programmed using Verilog HDL and simulated using Icarus Verilog. So what is this project? We built a digital simulation of Smart Toaster, not a real physical toaster, but a hardware model that behaves like one, controlled entirely by digital logic and Verilog code. The core of the system is a FSM, a finite state machine. Think of it as a strict rulebook. The toaster is always in exactly one of five defined states, and it only moves to the next state when the right conditions are met. But first, let's run our code. So here, our system has five out inputs. The first is a CLK, the clock signal. This is the heartbeat of the entire system. Every state update only happens when the clock ticks. In our simulation, we set it to 10 nanosecond cycles. It flips every 5 nanoseconds. Then the second input is reset. When this is set to 1, it doesn't matter when the state system is in. It immediately backs to idle. Think of it as a hard reset. Then the third is a lever down. When this goes to 1, it means the user has physically pressed the bread handle. This is what kicks the whole toasting process into motion. Then the fourth is a timer done. This goes to 1 when the toasting duration has elapsed. It's the system's way of saying the bread is ready. And the fifth is a cancel button. If the user wants to stop toasting early, this goes to 1 and the system immediately moves to the pop the bread. On the output side, we have four signals. Hold magnet. When this is 1, the electromagnet is active and the lever is locked down. Now the heater, when this is 1, the heating element is running. Then the pop, when this goes to 1, it triggers the spring to eject the bread. And now the beep, when this is 1, the buzzer fires once to notify the user that toasting is complete. Now let's walk through what each row means. Type 0, reset is 1. All inputs are 0, the state is 0, 0, 0, which is idle, and all four outputs are 0. The system is being held in reset. At the time 10 nanoseconds, reset drops to 0. The system is now live and sitting in idle, waiting. Now for the 20 nanoseconds, the lever down goes to 1. On the next clock edge, the state moves to 001. It's 1. Hold magnet turns on, showing 1 in the magnet column, but the heater is still off. One tick later, the state automatically advanced to 010. Toasting. Now both hold magnet and heater are on. It show 1. Now the bread is being toasted. At the time 60 nanoseconds, the timer done goes to 1. The state moves up to 011, pop up, hold magnet and heater, both drop to 0, and the pop-up becomes 1. So the bread is ejected. The next clock tick state moves to 100. So done. The pop-up goes back to 0 and the done beep becomes 1. the buzzer fires. And then the system returns to 000, idle. All outputs are back to 0. That is one complete normal toasting cycle. Now the second test cycle works the same way, except we use cancel button. Every single row in the truth table is proof that our FSM logic is correct. The right outputs are active for the right states, and the transitions happen exactly when they should. So here, our device is at reset, so it is in standby mode. And now in idle, the outputs and inputs are all 0. So the device is just waiting. Now when the lever is down, the next state will be 001. So what is the next state? The next states will be hold the magnet. So after that, the hold magnet will be 1. And after putting the bread, the next state will be heater on. So it just wait until the bread will pop up. So the next state will be pop up. So after popping up the bread, we're now going to the done beep. So the heater on is 0, the hold magnet is 0, the pop up is 0. So after that, the done beep, the cycle is done. Now it goes back being an idle, waiting for the next cycle. So the next cycle, we're gonna try using the cancel button. So idle, then first lever down, so the hold magnet, and then after hold magnet, the heater will be on. This one, the heater will be on. Now after the heater will be on, let's try using the cancel button here. So the cancel button is 1, so the rest, the after this will be done. As you can see, done. Then all the outputs are now in 0 state. I mean 0. Then after the done, it goes back being an idle again.
Time scale. Think of this like setting the unit on a roller before you measure something. 1 in S, you see, 1 in S means every 1 in our code 1 nanoseconds of simulation time, while 1 ps is the precision. The simulator can do math as fine as 1 picoseconds. Without this line, the simulator doesn't know how to measure time at all. And next is the main module, the toaster hardware blueprints. A module in Verilog is like a blueprint of hardware chip. Every time inside here describe what the chip does and what wire it has. Think of it like a drawing the box that represent our toaster in a circuit diagram. And leveling every wire that goes and every wire that comes out. So the first input is input CL key. The clock is the heartbeat of the entire system. It takes continuously 0101 like a metronome. Nothing in the system changes or moves unless the clock ticks. In our test bench, we set it to tick every 5 ns giving a 10 ns full cycle. While input reset, well, input reset is the emergency button. When reset equals 1, it doesn't matter what the toaster is currently doing. It immediately stops everything and goes back to idle, like unplugging the toaster and plug it, plugging it back in. And next is the input lever down. This is the sensor that detects when the user pushes the bread handle down. Lever down equals 1 means the handle is down, while lever down equals 0 means the handle is up. While input timer down, this signal goes to 1 when the toaster timer runs out. It is the system when saying the bread has been toasting long enough it's ready. In real life, this will be connected to an actual countdown timer circuit. And next is the last of the input is input cancel button. If the user changes their minds and wants to stop toasting early, this goes to 1 and the toaster immediately moves to pop and bread up, like pressing the cancel or stop button on a real toaster. And the output is the first of the output is output reg or hold magnet. Controls the electromagnet that physically locks the lever in the down position. Hold magnet equals 1 and magnet is on. Is locked down, bread stay inside. While hold magnet equals 0 and magnet is off, lever is free to pop up. Now, reg means see reg means this output holds remember its value between the clock ticks. And the next is the output reg heater on. Controls the heating elements inside the toaster. Heater on equals 1 and coils are hot. Bread is being toasted. And next, and heater equals on equals 0 and coils are off, no heat. And next is the output is the output reg pop up. Triggers the spring mechanism that launches the bread upward. Pop up equals 1 and spring releases, bread ejects. This only fires for 1 clock cycles, just long enough to release the spring. And the output reg done beep. Rings the buzzer to notify the user that toasting is complete. Done beep equals 1 and buzzer fires for 1 clock cycles. And next is the done beep equals 0 and equals the silence. And next is the state levels or mga parameters. Instead of remembering that 0, 1, 0 means toasting, we give each binary numbers as a human readable name using parameters. 3B means this is the 3-bit binary numbers. Think of this like naming the floors in the building. First, the ground floor or idle. Idle equals to 0, 0, 0. And next is the floor 1. Is the lower bed or 0, 0, 1. And next is the parameter toasting. Is the 0, 1, 0. And next is the parameter pop up or 0, 1, 1. And lastly is the parameter done 1, 1, 0, 0. And next is the state strategies. We need 2 memory slots to track where we are and where we're going. Each 3 is bits wide because our state levels are 3-bit binary numbers. State equals to current state where the toasted is right now. And next state, the planned state. Think of it like a 2 sticky notes in a whiteboard. See? One says current floor toasting, while the other says next floor is pop up. When the clock ticks, the next note becomes the current note. And next is the block 1 or memory block. This block is responsible for one thing only, officially moving the system from its current states to the next state. Always means of this is always patch age CL key or patch age reset means this blocks only runs when the clock takes from 0 to 1 or when the reset takes from 0 to 1. Think of this like a security guard standing at the state door. The guard only moves when the clock bell rings. When the bell rings, the guard looks at the next state, sticky note, and update the state sticky notes to match it. See, and if reset is active equals to 0, 1, ignoring everything else. Immediately write idle onto the state sticky note. No matter where we are, even if we're in the middle of testing, everything stop and where we go, where we're back to the beginning. For else, normal operation with the clock ticks. Copy whatever is on next state on the state. This is the moment the system officially changes state. The this is well this symbol means assign the next clock edge or non-blocking. For after that after that always it means of always this all means meaning always means runs these figures out where to go next based on the current state and inputs. Well, you see always means runs this back instantly and continuously. The moment any signal changes, lever down, timer done, cancel button or state, this block immediately recalculates next state. Next is think of this like a navigation app that constantly recalculates your route. It doesn't wait for the clock, it updates in real time. And next is the always you see this is a case state. Case is like a switch statement. It locks the current state and picks the matching role for what to do next. For idle, beginning, or begin, is we are waiting did the user push the lever. For for else for else next. Else next. Else is next is idle. Lever down. Lever down equals to 0 and no one push anything and stay in idle. Bread. If you see this, it means this. Next is the lower bread. Lower bread or see this bread is being lowered, no decision needed here. Once the bread is lowered, we always go straight to toasting. This transition is automatically no input required. For toasting, we are toasting. We stay here until one of two things happen. For next state for pop up timer done equals 1 and bread is ready. Time to pop it up. Cancel button equals 1 and user stop it early, pop it up anyway. Either condition sends apps to pop up. For next is to text. For else for next state equals toasting is neither happen yet, keep toasting, stay in toasting. For pop up, bread just ejected. Automatically move to done to sound the beep. No input needed. Popping always lead to the done signal. For done is beep just fired. Automatically return to idle. The toaster is ready for the next round. Next state of default is safety net. If the hardware glitch somehow puts in a state that doesn't exist like a binary or 101 or 110 110 or 111, this catches it that forces us back to idle. This prevents the toaster from getting stuck forever. For block 3 is the combination. For the combination is always begin. This block decides which output to turn on based on only the current state. This is what makes our design a smart machine. All output depends only in the current state, not on the inputs. No matter what the user is pressing, the output are always determined by which state we are currently. For this is for always, if you see, always, just like a block 2. This runs instantly whenever state changes. For always begin, default turns everything off first. Before deciding to what to turn, we reset all outputs to 0. This is the very important. It prevents an output from accidentally staying on from a previous state and previous state when we do not want it anymore. Example is what without this heater might stay on ever after we lost this toasting. For case state, now turn on the only what belongs in each state. For hold magnet, the electromagnet turns on to clock the lever in the down position. Without this, the spring will push this bread back up immediately. Heater on stays 0. We do not heat yet bread isn't fully loaded. For toasting begins. For toasting, magnet stays on. We still need to keep the bread inside while toasting. Heater turns on. This is where the actual toasting happens. Both signals are 1 at the same time during this state. For pop-up begin, pop-up, magnet is off. Is to 0 is off. 0 from default. Lever is now free. Now it's now free. For free hand. Pop up bars to release the spring and launch the bread upward. Heater is always off. No need to heat anymore. For done, for begin, all other outputs are off. Only the buzzer fires for exactly one clock cycle to signal completion. Next clock takes state goes to idle and then deep beep goes back to 0. Idle has no keys here. It uses the default above. And idle, the toaster is completely quit. No magnet, no heat, no deep, no beep. And that's all.
Test bench module. The simulation test environment. A test bench is not real hardware. It has no input or output ports. Think of it as a fake lab setup. A person sitting in front of the toaster, pressing buttons and watching what happens. The test bench does these three things. First, generates the clock signal or heartbeat. Second, manually drives input signals or simulates button presses. Third, observes and records the output signals. So, module theory, module theory smart toaster, signal declarations. Inputs declares as red. We use red because we need to manually assign values to these signals. Red means the simulator will remember and hold the value we give it until we explicitly change it. Think of red like a physical switch. You flip it to 0 or 1 and it stays there. Uh, our output declares while. So we use while for outputs because we are not controlling them. We are just watching what the toaster module sends back. A wire automatically carries whatever value is being driven into it. Think of wire like a light bulb. You just watch if it turns on or off. So here we instantiate our smart toaster module. Instantiating means bring the blueprint to life inside our simulation and plug all its parts into our test signals. This one stands for Unit Under Test. That's just the nickname we give to the instance of the module we're testing. The dot notation connects ports. That's CL means connect the module CL port to our test bench CL log. This one. And reset means connect the module's reset port to our test bench red reset. And so on for every port. Clock generation. This line generates the clock signal for the entire simulation. This one. Wait 5 nanoseconds to flip the clock. 0 becomes 1 and 1 becomes 0. Wait another 5 nanoseconds, flip again, and repeat forever. This creates a continuous square wave. 0 nanoseconds to CLK equals 0. 5 nanoseconds, CLK equals 1. Rising edge to post edge. This is when black one triggers. And 10 nanoseconds to CLK equals 0. 15 nanoseconds CLK equals 1 is rising edge again and so on. Full cycle 10 nanoseconds. This is the heartbeat of the simulation. Always number 5 CLK equals CLK. Waveform done for GTK wave. This block saves all signal changes during the simulation into a file called the toaster.residue or value change. Once the simulation runs, you open toaster.residue in GTK wave and it draws a visual timeline of every signal like a graph showing when each wire went from 0 to 1 and back to 0 throughout the entire simulation. Dot bars, this one, record all signals in the test bench. And this one also record all signals inside the toaster module. Test this sequence. This is the main test script. It's like a step-by-step instruction sheet that tells the simulator exactly when to press each button. Number 10 means wait 10 nanoseconds before doing the next thing. Uh, we run two test scenarios to cover both ways dosing can end. So initial begin. The truth table header. These display lines with a formatted header in a terminal. It labels the columns of the truth table we're about to see. So the this one is like a security camera that watches all signals at once. Every time a realistic signal changes value, it automatically brings a new row. We don't have to ask it to print. It does it on its own whenever something changes. And this %p means print the value in binary 0 or 1. And %t means print the current simulation time. And let's on this one, let's speak inside the toaster module and read the state register directly. Initial setup. Initial setup time 0 nanoseconds. Set all signals to their safe starting values. Reset equals 1. Reset equals 1 means the toaster is held in reset mode. It won't do anything yet. All other inputs are 0, no buttons pressed, no timer run. Release set time to 10 nanoseconds. This one. Wait 10 nanoseconds, then turn off the reset signal. The toaster is now live and sitting in the waiting for someone to use it. So that's right. Normal toasting cycle scenario. User puts bread in, toast in, timer finishes normally. So our expected path is lower idle to lower bread to toasting to pop up to down and to idle. Number 10, this one, never down equals 1. Wait 10 nanoseconds then simulate the user pushing the bread handle down. Never down goes to 1, 2 on the next clock tick. State moves to the lower point. Then number 40 timer down equals 1. Wait 40 nanoseconds. This simulating bread cooking. Then fire the timer signal. Timer done +1 tells the toasting state that the bread is ready. On the next clock tick, state moves to pop up. Number 10 timer down equals 0. Wait 10 nanosecond, then turn off the timer signal and release the lever. The system continues to pop up, to down, to idle on its own. In number 30, wait 30 nanoseconds, just giving the system time to cleanly finish and settle in order. No inputs needed here, we're just watching. So press to the console button. The scenario here is user puts bread in but cancels toasting before the timer finishes. So our expected path is either to lower bread, to toasting, to pop up, to done, and to either. Same exact path, but different trigger. Trigger. Cancel instead of timer. Number 10, lever down, wait 10 nanoseconds, then push the bread handle down again for a new brown. Then wait only for 20 nanoseconds, this time simulating the user panicking and pressing cancel. Before the toast is done, cancel button and one exits toasting immediately. And for this one, wait 10 nanoseconds, then release the cancel button with the lever. System flows to pop up, to down, to idle on its own. The number 50, wait 15 nanosecond watch system, return to idle completely. And simulation, uh, finish tells the Icarus Verilog simulator to stop running. Without this, the simulation would run forever. The clock never stops.
And that's basically how our smart toaster FSM works, from the code all the way up to the simulation output. To quickly recap, the system starts in idle, waits for the lever, locks the bread down, heats it up, pops it out, beeps, and resets. Back to the beginning. 5 states, and every output is driven by exactly which state the system in at that moment. The three always block each handle one job. One locks in the current state on every clock tick, one constantly figures out where to go next, and one controls what turns on or off. That clean separation is what keeps the whole design organized and easy to follow. And through the test bench, we verify the full cycle twice, the normal toasting path and the cancel path, and confirm every signal behaved exactly the way the FSM diagram says it should. So whether the bread finishes naturally or the user cancels early, the system always handles it correct and always find its way back to idle. And that's all. Thank you.